Okay, here we are, chapter 15, the last chapter. This is about properties of gases. This is a very short chapter as opposed to the last one, which was quite long. Here we're just going to look at some of the simple relationships between the various properties of gases, Boyle's law, Charles' law, and the combined gas law. So first of all, we have Charles' law, and that simply tells us that the relationship between temperature and the volume of a gas is direct, which means when the temperature goes up, the volume goes up. When the volume goes up, the temperature goes up. This is the relationship. So when we have a shift, so you see here this ratio, and this is how we're going to solve it mathematically. Say we've got 50 liters of a gas at 100 degrees. If that gas expands from 50 to 100 liters, that means the temperature must have gone up. On the other hand, if the volume of the gas decreases, that means the temperature went down, right? 50 over 100, 25 over 50, that would give us the same ratio. So some examples of this would be a hot air balloon, right? In a hot air balloon, the temperature of the gas goes up. We light the burner, we heat up the gas expands, takes up more space, it has more volume, but the same amount of mass, and therefore its density goes down, making the gas inside the balloon less dense than the gas outside of the balloon, giving the hot air balloon buoyancy relative to the surrounding air. Um, Other examples, if you take a ping pong ball, one of these strategies, if you get a ping pong ball that gets smashed, you can put them in boiling water, and that will cause the gas inside the ping pong ball to heat up. As that gas heats up, it will expand and it will pop out the dent, and then your ping pong ball will be restored to its original shape. The idea of taking a balloon outside where it's cold, whether it's a helium balloon or any other kind of sealed balloon, take it out in the winter when it's cold outside, and that gas temperature will go down. Therefore, the volume of the gas will go down and the balloon will shrink. Yeah, those are all good examples of Charles' law. It's the relationship between temperature and volume, and you need to have the absolute temperature, the absolute temperature. See, it would be very problematic here if we stuck in, say, 0 degrees Celsius, because that would cause this fraction to fail miserably. So we need to use the absolute temperature, the Kelvin scale or the Rankine scale. Doesn't matter which one you use, as long as you're consistent with your two temperatures. Because going from 50 to 100 degrees Celsius is not really a true doubling, right? Going from 50 to 100 degrees Kelvin is. So we've got to use an absolute temperature scale. We learned about that last chapter, the difference between an absolute and a relative temperature scale. Can't have negative signs in this ratio. It's going to goof everything up. So can't use Celsius, can't use Fahrenheit, got to use the absolute scales. You can rearrange it to have the ratio of the volumes on one side and the ratio of the temperatures on the other side. Same effect. All we've done here is cross multiply and divide by the other product. So that was Charles' law, temperature and volume. Here we're going to talk about Boyle's law, which is pressure. Pressure and volume if the temperature is held constant. So we've got to understand that that's a precondition for using Boyle's law, just as a precondition of using Charles' law was that the pressure was going to stay constant, right? The balloon that's taken outside, the atmospheric pressure is the same outside as inside, so that part was not changing. So mathematically, this is going to look a little different because it's an inverse relationship. As the volume goes up, the pressure goes down. As the pressure goes up, the volume goes down at a given constant temperature. So some examples of this would be a syringe, right? If you seal the other end of the syringe and you push the plunger in, the volume is getting smaller and the pressure of the gas inside is going up. Similar with the bicycle pump, we push the plunger down, that causes the pressure to go up, that causes the air to be pushed into the bicycle. We talk about people's lungs, right? So your diaphragm drops, that increases the size of your lungs, the volume goes up, therefore the pressure of the gas goes down, therefore the pressure in your lungs is less, the pressure outside is more, and the air comes in your nose, in your mouth to fill up your lungs. This is all due to the fact that your diaphragm, this muscle below your lungs, drops down, causing a partial vacuum, causing the gas to expand and the pressure to drop. So all examples there of Boyle's law, the relationship between volume and pressure. Here, it's not as critical. We don't need absolute temperatures, and we can be using relative pressures as long as we're consistent with our use of that pressure. The density pressure relationship, this is the third one. It doesn't exactly have a person that it is named after that I'm aware anyway. The density of the gas is directly proportional to the pressure of the gas. So this is the density. How many gas particles do we have, and what does that do to the pressure? So the density ratio to the pressure ratio, as the density goes up, the pressure goes up. As the density goes down, the pressure goes down. That's what direct means. They move in the same direction. So again, you can rearrange it to write it as multiplication instead of division if you would prefer. A great example of this is bicycle tires, car tires, right? When we want to blow them up, what do? We just pump more gas into them. We pump more and more gas, more and more particles in there, making the density higher and higher. And that makes the pressure high enough for the tire to do what we want it to do effectively, allowing us to roll along the road. So finally, we have what's called the combined gas law. So we had Charles' law, which was assuming a constant pressure, Boyle's law, which was assuming a constant temperature, each relating to objects or two variables. So if we combine them and no longer have a requirement for anything to be constant, then we have pressure, volume, and temperature all together in a single expression. So this gets more complicated, right? Instead of 4 variables, now we're dealing with 6 variables, but they're familiar variables, hopefully. When we do this, both the pressure and the temperature have to be using the absolute scales. We already talked about that for Charles' law, what that means for temperature, that we use Kelvin or Rankine, and that we not use relative pressure for our pressures, right? It's very, very common for people to talk about something being pressurized slightly above atmospheric or slightly below atmospheric pressure. That is not acceptable in this case. The pressures need to be entered as the absolute pressures, right? If you're a little above atmospheric pressure, say you're 15.1 pounds per square inch, people might, write that or record that as 0.4, plus 0.4 because it's 0.4 psi above atmospheric pressure. Can't do that here. You got to go ahead and put in the 15.1 psi for the pressure. Here, the relationship's a little more challenging to understand. It's not simply direct or indirect because there's 3 variables on each side. And that's where, it's really nice to use Charles or Boyle's. If we can get one of them to stay constant, then the relationship is easier for us to evaluate. But we can solve this mathematically. If we are given 5 of the 6 variables, we can plug them in and solve for the unknown. We often talk about something called standard temperature and pressure, which is abbreviated STP, or standard temperature and pressure. The standard temperature and pressure is 0 degrees Celsius, that's the standard temperature, and the pressure is the atmospheric pressure at sea level, which is 101,000 pascals or 101 kilopascals. Remember, kilo is a prefix that means thousands of pascals. So under these conditions, under a standard temperature and pressure, we would have, if we had exactly 1 mole of gas, which is simply a number of gas molecules that we like to use in chemistry and in physics at times. It's like a dozen or 100, or it's just a number of the molecules. So if we're at 0 degrees Celsius and at atmospheric pressure at sea level, that 1 mole will have a volume of 22.4 liters. Again, this is important, right? This comes from our density discussion, right? If we had had twice as many gas molecules, then the volume would look different at this temperature and pressure. So these are the various equations that you're going to do some math problems on in this chapter. Again, this is a short chapter. Now we're going to talk about a couple other concepts. One of them is vapor pressure. So when you have a liquid sitting in a container or somewhere, some of that liquid is going to evaporate, and that's going to add gas molecules to the gas that was already above the liquid. And that contribution is considered the vapor pressure of that liquid. Some liquids have a high tendency to vaporize and to turn into a gas, and some have very low tendency, right? Even within the petroleum products, gasoline it tends to evaporate very quickly versus fuel oil tends to not. So you've got that differential between the two of them. Due to this increase in the pressure, the vapor pressure is raising the pressure of the gas above. This can cause things to be affected by this change in pressure. For one thing, we have something like a pressure cooker, right? Where we are boiling water in a sealed container, and as more and more of that water turns into gas, the pressure on the remaining liquid goes up, and it makes it harder for that liquid to turn into a gas because there's already so much pressure above it. That makes the water boil at a hotter temperature, which allows us to cook the food that's in the water at a higher temperature, which is why we have such constructions. We don't make pressure cookers just so they can accidentally explode and cause damage. We make them for a reason, and it's to raise the cooking temperature so we can cook the food faster or in some way better. On the flip side of that, you can also have low pressure, which reduces the boiling point, right? In Denver, where you're a mile above sea level, the atmospheric pressure is less. The water will turn into a gas at a lower temperature. So water actually boils below 212 degrees Fahrenheit, below 100 degrees Celsius in Denver. And as a result, it will take you longer to boil your eggs. It will take you longer to cook your pasta because the water is boiling at a lower temperature. Therefore, less energy is going into the food. Therefore, the food is cooking slower. And you can see that in cookbooks. They will give instructions like add 30 seconds to your boiling time for every 1,000 feet you are above sea level, or something to that effect, to take into account the fact that the water is boiling at a lower temperature and you need to cook it longer to get the same energy delivered. As we discussed last chapter, condensation is the opposite of evaporation. So when you have a lot of water vapor in the air and the temperature drops, then you can get that water vapor condensing out of the air. This is where dew comes from every morning. This is where frost in the winter, right? It condenses and then it freezes and becomes ice. Because the sun has been down and the ground has cooled off, and you get warmer, moisture air that comes in and touches that cold ground, and you get this condensation. So there's this point that's called the dew point, at which the water vapor will start condensing out of the air and into a liquid form. Fog will occur when that dew point is reached over a large area, right? Not just right on the surface, but in the air, the temperature has dropped enough, and so you get water condensation in the air, and you get all these little droplets of water, which then are visible, right? The gas was not visible, but the liquid is visible. That's why you can see clouds. Clouds are droplets of liquid water. And that fog is essentially a cloud that has formed near the surface. Normally, the clouds form way up in the sky where the air has cooled off because it has expanded and used up its energy. But sometimes, in the right conditions, the fog will occur near the surface. And the fog will almost always go away as soon as the sun comes up, because the sun warms the air, warms the ground below the air, and that causes the water vapor to evaporate. Humidity is this measure of how much water vapor is in the air, and we have something called absolute humidity, but we are far more interested in what's called relative humidity, because we as humans regulate our body temperature by sweating, by evaporating off moisture. And if there is already too much water vapor in the air, then our sweat will not evaporate effectively, and therefore we will not be cooled off and we'll be very uncomfortable. Now, the absolute humidity varies based on temperature and pressure. So in the winter, the absolute humidity is actually quite a bit lower than it is in the summer, but we don't care about that in the winter because our body isn't trying to cool itself off in the winter. So we care about the relative humidity. We care about how much more humidity can go into the air, right? Because that's what we want. We want our sweat to evaporate, and that will cool us off. So when you start to get the water vapor close to the maximum amount that can be held, then it's harder and harder for sweating to take place. It's harder and harder for a liquid to evaporate. And actually, you don't have to be all that close to 100%, right? As soon as you get over 50%, that starts to make your sweating less efficient, less effective, and it starts to become uncomfortable to us. Again, the people in Arizona are very proud of their dry heat because the water evaporates off of us very quickly, and our cooling mechanism works, and so we tend to feel more comfortable but then you can get, dehydrated. So once you get, above 50%, especially above 60, 70%, your sweating starts to be affected and you really feel that hot, clammy nastiness that we don't like in the month of August, which is almost here, right? That's the end of chapter 15. Again, we'll have an exam and then this class will be concluded. There is no final exam in this class, just the 5-unit exams. And when you've taken that last exam over chapters 14 and 15, you will be done.